here. Welcome back. This afternoon, we're going to dive pretty hardcore into circuits. And so I want to start with a little disclaimer that this is one of those things that for me, I could justify kind of spreading this out over a couple of blocks because there's a lot of material in there. If you don't have any experience at all with reading a multimeter or a breadboard, and then on top of that, using Tinkercad, you've got physical simulation, builds, you've got simulation builds, you've got a lot of moving parts right here. So this is a unit that I really, let me turn that off so it's not running in the background. Try to spin it down a little bit and really make sure that I'm scaffolding it for my kids. It's really important for me specifically because I teach digital electronics that my kids have a very good foundation of this basic circuit stuff. And especially how does a breadboard work? How does a multimeter work? Just in order. So when they get in that class, because that class, I think if you actually look at the day-by-day plans, DE has about 8 or 9 more days in it, built into it than POE does. And we are, already maxed out in POE for what we do here in Arkansas. And so that's without an assembly day or and I think, Brendan, if you looked at the actual DE day by day, it's 3 days for the breadboard or the birthday problem, right? He's laughing because that's hysterical, right? Yeah, maybe 3 full class days, right? I mean, that's a big project. And so, just kind of be thinking about that. So how much time do you want to spend on these may depend on, what you've got going next. So you can kind of scale this up or scale this back a little bit. But I have found that the way that I try to lay this out for my kids is we're going to teach the basic concepts of DC circuits. We're going to talk about current and voltage and resistance. How do those things relate to each other? Once again, this is one of those things that if a kid understands, that current and resistance are inversely proportional to each other. If the voltage is constant, that's a win, right? And if they understand that, voltage and resistance are proportionally constant if the current is the same. And so and then they know the formula. So I really spend a lot of time asking my kids about what's going to happen if we increase the current here. What would happen if we increase the resistance here? Because I want them to try to understand it because then they know the formula and I feel a lot more comfortable about them getting the math right. And so one of the things, and I don't know that I've said this yet, but I say it a lot in class is, to ask kids, does your answer make sense? So, I've got a funny meme somewhere in a slideshow and I don't know where I found it on the internet. It's like 68% of all, engineers don't trust the first number their calculator gives them, right? And so so many times you've seen kids, if you've been in education, you see kids punch something in a calculator, no matter what the number is, that's what they write down. They don't even pause to think about, does that answer make sense? So on this, there's some rules and some things that we can kind of go through to kind of help them catch those, hey, that answer doesn't make sense. So I'm going to talk about those and try to get my kids to understand this conceptually, be able to feel comfortable doing the math. So I make sure that I show them how to put stuff in the calculator on a couple of these. And I've got little whiteboards in my classroom. I got a class that they're 8.5 by 11 or 8 by 11.5 or whatever that is, the same size as like a sheet of paper. And they're real good way to check for understanding for me. When I'm lecturing and we're working on problems on the board, I can have them write down what they got and hold it up and I can look around the answer and go, oh, Caleb didn't get that. Let's go over and see what's going on. Did he just, most of the time it's they probably flip the things and, divided when they should have multiplied or numerator, denominator backwards and then the other thing Project Lead the Way will do constantly in these is, well, you just the kind of the nature of the beast with this is you've got to switch back and forth between unit, SI prefixes from milli to amps, so there's some of the kids still struggle with that. So how do you want to teach that? You do dimensional analysis? Do you teach them just to multiply by, how do you want to kind of handle that? Because there's going to be some kids that struggle with that. All right, so let's, without further ado, do we have any questions about anything from block 3 submission form that are still lingering that might apply to the whole group that we could wrap up real quick? Well, let's get rolling here. So where we're going to be starting today is with block 4 here. And so I wanted to show you I should have had this pulled up. I wanted to show you just kind of where we're going in the submission form for this. And so let's go to courses, and we're going to go to the one for our core training. There. Nope, that's the wrong one. Oh, too many clicks already today. There it is. They're both white, but that one's okay. So here we go. So block 4. There's the submission form. So let's look at this because there's a couple things, and I want you to make sure you pay attention to this as we kind of go through this, because there's a couple places in here that are just a little bit confusing, and it's not necessarily, I don't have a revised one. But so there are different versions of the same activity. So you'll notice that it starts out talking about the physical build of 1.2.3. So this is the one that you guys are going to use your breadboard on and build. They gave you guys a button, right? You do not need to use the button, okay? You can save the button and throw it away. I don't care, because here's what happens is you're trying to show me a picture, take a picture of your cell phone or a video or whatever of that circuit working and the reading from the multimeter all in one shot. And if you've got to do that and hold the button, most of you don't have 3 hands. And so I haven't figured out a real good way to do that yet. So by taking the button out, it makes it a little bit easier for you guys to do that. So do not worry about putting the button in your circuit, okay? When you build those, if you want to, that's fine, but you do not have to do it. I wish they would have gave us a switch, so you could have done it kind of hands-free, but they didn't. So don't worry about that. But you're going to be doing a physical build. So these, when you're actually breadboarding, what I'm looking for is, can I tell that the circuit's on? And, you know, if you've got to measure something, can I tell, you know, can I see the multimeter reading that shows me, you know, that you've got it correct? So, you know, some kind of pictures in here for those. And then when you get down here to it's your turn, you're going to be building those same things in simulation. So it's the exact same activity. So you should be able, so all your numbers should kind of match. They should be really close for what you're building. So then you look at that, and then we've got, where is it? Right under the it's your turn. I want to pay attention to this too. Insert a screenshot of your series circuit from procedure step 20 in the alternate activity. That's a, if you don't catch that alternate activity, that'll throw you for a loop there. So make sure you catch that right in there, that this is the alternate activity 1.2.3, okay? And then simulation, and then you've got some circuit calculations, and all those things match up. So it seems like a little bit more, but you know, basically you're building the same circuit, you're doing it physically, you're going to do it in Tinkercad, and then you're going to do the math for it. So if you do the math first, you should already kind of know what your readings should be. So just kind of food for thought on that. And that's actually the way that we do this in my class, is I have the kids go through and we do the math first. Okay. All right. So you should have some of these things in your kit. And let's get started. I'm going to spend a little bit of time just going over electricity, and there's a PowerPoint that's fine. You know, there's absolutely nothing wrong with the PowerPoint that's in here for circuits. It starts by really kind of talking about some of the very basic stuff with electrons in this introduction to electricity. It talks about, you know, kind of some stuff with different examples. This is a really nice chart right here for the kids to understand, you know, what are the different things. I've got one I'll show you that I kind of write in a little bit, but they get confused about this because the SI symbol and, you know, the abbreviation, the variable that we use in the formula are, you know, the same for voltage, but they're different for current and resistance. And so that messes the kids up a little bit, but you can kind of look through this and it kind of gives you some formulas. I'm going to give you some additional formulas, but it talks about series. You got a little T chart here. So normally in lecture, I cover all this stuff as we kind of go through, and then we work some examples and I'll show you how we do that. So be prepared as we go through this to have a sheet of paper out, because I'm going to give you step-by-step instructions on how to solve these problems. And then we'll go over how to measure some stuff. All right. All right. Let me share my deal here with you. Did I hit the, I need to make sure that I hit the recording button. Stop my share real quick. Yes, I am recording. Okay, good. Okay. Get that there, camera there. All right. So, you know, these are the calculators that I keep in my class. They're 11 or 10 bucks, and they'll do everything we need to do for engineering, all our trigonometry functions. They've got our probability function on there as well. If you have a fancier calculator, that's not a problem. But I'm real big with my kids about not letting them use their cell phones for their calculators as they go through class, because on their exam, they can't use their cell phone for me. And so they need to be able to know how to use either the calculator they've got or the one that I provide for them. And when we start doing some of this stuff, these are a little bit cleaner than trying to do it on the iPhone or, you know, whatever you've got. All right, let's talk about Ohm's law first, okay? And if I've got it up still, there it is. I've got a little meme for you to kind of think about. And please chime in if you've got something to add. I know we've got people that in here that teach AP Physics and engineers that probably know way more about electricity than I do. Or is, you know, DC jokingly called pixies, AC, angry pixies. All right. So I like this little meme that you can talk to your kids about. And the way that, you know, we think about an amp is current, you know, the amount of, you know, flow. Voltage is the kind of the force of that. Also, maybe I kind of think about it as the potential energy difference between the positive and negative terminals. I've gotten in trouble saying that from some AP Physics folks in the past, but that's the kind of the analogy that I'm gonna use for my kids. And then the resistance is like, you know, the faucet. That's the easiest one for them to get, but we'll talk about these. And so I might talk about, you know, the Arkansas River here where I live is big and wide. And so like right now, you know, it's kind of running slow, but it's got a lot of water in it. So I might have a lot of current, you know, I might have a lot of flow, but it's not moving very fast, which would be the force that's kind of pushing it. Up in Colorado, where the Arkansas River is kind of born, you know, I've actually straddled the Arkansas River. And so there, you know, it's really running pretty fast. So it might have more force, but not as much current. So that's kind of one analogy that I use. We're going to use water a lot with this as they go through, but I really like that. You can find that on the internet for Ohm's law. And so I'm going to start out with my kids and I'm going to have them write down this a little triangle. And so we talk about that voltage, right, is going to be a variable V in our math formulas. And what does, you know, what is it measuring? You know, it's measuring volts. And then what is the SI symbol for that? So, you know, if you measured 37, what are you going to put after that? Well, you're going to put that. And so there's current and what we call it, right? And then amps is what the SI unit of measure is. And then what's the symbols in A, and then ohms is the Greek letter omega. So that kind of helps my kids kind of break down some of those. And it's very similar to what Project Lead the Way has on that chart. Either one is fine. But I want my kids to kind of understand, you know, that. Now, if you're having kids type in stuff to turn in work, you know, a lot of times I just have them type out ohms. I don't make them go find the Greek omega. And you can do that. Brendan, you'll like this. I did finally figure out this year how to do the bar above letters for DE for when they're typing Boolean, like equation.
I've never figured it out. I always just use a comma.
Yeah. I had a kid. I assigned that for bonus points and a kid figured it out. But yeah, I still use the sky comma. All right. So I was telling you guys that we have a dam. Okay. And I was telling you that, so this is a picture of my dam here, the Lake Dardanelle Lock and Dam. And so behind the lake, right, is water. And then on the downstream side, right, is a river that's coming out. So if you think about that, when we're talking about just basic kind of electricity in this sense, is that the dam is serving as the resistor, right? It's resisting the flow of that. The bigger the dam, right, the more resistance, the higher what we would call a head on a dam, right? The distance between the surface of the lake and the river. And so we can measure those things, and we can say almost like this is like potential energy. So I can talk about voltage. If I measured, and you guys know that, like if I had a bowling ball sitting on a shelf, I could take its mass and its distance from the floor and find out how much kinetic energy, potential energy it has. And so the same thing here. So we can kind of think about voltage as that force or the difference between like the positive and the negative. So I could measure this distance, right? And I could see, you know, what my voltage is. And if we go back to our Ohm's law, you know, if we're looking in terms of current, right, then voltage and resistance are proportional. You know, if current is steady, then, you know, if current is 100, you know, and this is 1,000 divided by 10, well, then if this stays current, then these things have to move with each other. So they can kind of think about that. And then I said, well, in a series circuit is maybe like a bunch of resistors right in a row. So if I had, you know, the Arkansas River, the Mississippi River, any of those, you know, it's not just one dam, right? It's a series of dams. So I've got a dam here. And then if I go down to the next town, there's a dam. And then if I go down to the next town, there's a dam. And so I have a series of locks and dams. So I've got, you know, that kind of do this. And what I could think about in this is if I took the total height of this whole system, the potential energy difference from the very top all the way down here in a series circuit, this would be my voltage total. So my voltage at each, or my resistance, either one, I can add them up. So I could take the same thing. If I had, you know, resistor 1 and resistor 2 and resistor 3, I could just add all those things up. The same thing with my voltage. If I took that potential energy difference between here and here, you know, if I measured that, and then I did the same thing here and here, and I measured that, and then I did the same thing, I added all three things here, right? We would see that it's equal to that height. So when we go back, and stop me if you have any questions, but we're going to talk about in a series or just one path that our voltage total in a series is going to just be the voltage total. Like we're just going to add those things up, the potential energy difference across our different components. And we're going to be using resistors as our primary component. So I can say the voltage at resistor 1 plus the voltage at resistor 2 plus the voltage at resistor 3. So I could, or however many I had, you know. So I kind of use a ... for that. And then I can say, well, we talked about that resistance there, and I can say, well, my resistance total is the same thing. I just add those things up, R1 plus R2 plus R3, how many of those I got. Okay. So that's the way that the analogy that I kind of use with that for talking about a series circuit. And then we get into current. Okay, and so I'm going to talk about current with a different kind of drawing. And you guys, every time I draw this on the board, the classroom that I teach in is, I had art in that room when I was in high school. And I can think about Mr. Hines just cringing every time I draw on the board. So we've got a mountain range. That's the best one I can do. And off of that mountain range is a river. Okay, we said we used water a lot. So I'll switch colors. I'll move, my river's gonna be green. And that water is gonna flow all the way down to the ocean, right? Or to the sea. All right. So it's gonna flow all the way down there. And if you've ever, like I'm a whitewater enthusiast. I like kayaking and canoeing, and they measure the amount of flow in rivers in cubic feet per second. So if I came up here and I measured this, and now here's the deal about this river is that there's no tributaries coming into it. It's almost like it's in a pipe. It's in a sealed container. So whatever goes into it has to come out of it. Okay, so that's kind of where you have to think about that. So there's no tributaries flowing into this. When we put current in the river, it's always going to be, there's no evaporation, no nothing. So if I came here and I measured it and I said, well, it's 100 cubic feet per second. And if I came down here right before it ran out into the sea and I measured it there, I would say, well, it's also 100 cubic feet per second. So it doesn't matter where I measure it at, it's always going to be the same. So when we go back to our series path and we talk about current total in a series, it's always going to be the same. So my current at resistor 1 is equal to the current at resistor 2, which is equal to the current at resistor 3. Okay. So those are the laws for this. And then I say, well, what about current in a parallel circuit? Well, if I took this same thing, but I added, that white up here. But let's say that I came right here and I put another mountain range, and that river had to run into two different branches. One branch had to go around the east side or the west side of the mountain like that. And the other branch had to go around there to reconnect. And let's say I came over here and I measured the current in this branch and I said that it was 60 CFS, right? Well, it's still 100 going in, it's 100 coming out. If I've got 60 in this branch, what's got to be running through the other branch? 40 CFS, okay? So, because these are parallel paths, right? So when I look at my formula for current in parallel, current total in parallel, it's going to be additive. So I'm going to say the current at resistor 1 plus the current at resistor 2 plus the current at resistor 3, okay? Questions about what anything I've said so far? Okay. So I'm going to draw a very simple series circuit with some resistors for the symbols for resistors. And then I'm also going to draw one in parallel. Okay. Same thing, like 3 resistors. What I like to do with this one, I get a couple of resistors here, is I like to draw one side in red. I like to say that's my positive side. And I'll draw the other side in blue, just because I already did the things. Then I'll say this is my negative side. So those are all wires. So basically what happens here on this is that this thing, a parallel series is like, in the way that I've drawn this, it's like a coin. There's a heads and a tails, a positive and a negative side. So when I'm using, if I said, if anybody's ever measured, let's say this is a 12-volt battery, all right? And I take my multimeter and I come here and I measure that and I get 12 volts, right? All right, Tim, what happens if I'm measuring here? What happens if I could measure this wire here? What would my measurement be?
It'd still be 12 volts.
Mitchell, what happens if I slide it a little bit further? What happens here? He's got to put on his headphones. Or get his mic where he's working. He's muted.
It would still be 12.
Still be 12 volts. Get ready. I'm calling on you. All right. So let's see, Kayla, if I moved it right here, what would it be?
It should drop, right?
Is there
No.
any difference in this wire? Am I still touching the same wire?
Oh yeah, never mind. It should stay the same then.
Very good. That's what we, so if I now, so this is what we're trying to get. So Chad, if I move this up this wire a little bit towards that resistor, what's my reading going to be?
Still 12.
Okay. So I'll pick on Brendan. I know he knows it. So if I, Brendan, if I had that one here and I move this one here, what's my voltage going to be? Trying to,
Still 12.
still 12. All right, Jordan. Now, if I got it here, what if I move this one down here, like to right there down the wire? In the same circuit. What do you think that's going to measure, Jordan? He may have stepped away for a minute. All right, who haven't I called on? Let's go, Steve.
Alex, we're gonna go with what is 12?
There we go. So what I do, and I kind of draw this out with my kids because I want them to understand that it doesn't matter where I measure on this parallel circuit. If I'm measuring from one side to the other, it doesn't matter if I'm measuring here or here or here or here or here or here or here. All these different combinations are still going to give me 12 volts because I'm measuring the potential energy difference. I'm basically measuring the height of that total dam, right, from one side to the other. So when we go back to our formula sheet, we can look at this and say our voltage in parallel is going to be always the same. The voltage at resistor 1 is equal to the voltage at resistor 2 is equal to the voltage at resistor 3. Okay. Now, the last thing that happens here is the resistance in parallel. All right. And this is the formula that's the funny one. And that's what I tell my kids. I'm going to tell them the formula you have in your formula sheet, I don't like. I think it's trash. I think it's a terrible way to do it. This is the one I give my kids. I was going to do that in blue. This is the one I give my kids is we're going to do this. We're going to take resistor 1 inverse plus resistor 2 inverse, plus resistor 3 inverse, and then we got to take the inverse, all that. So that's the one, that's the easiest one. It's the least button presses, right? It's the least button for the, and like I said, I'm gonna try to teach my kids to be a little bit lazy, right? You know, if you can do it. So, but I also, and I don't always show the kids this, it just depends on if I think I'm going to confuse them. But like the formulas that you have in the formula sheet, I think are these first two. These are the ones kind of Project Lead the Way gives you. I like, of these two, I like the bottom one better because you can put this in your calculator in one spot and it gives you the resistance total. Okay. I don't like things that are two-step in my calculator. I want to put it in there and hit the enter button and it give me the right number. Okay. So then you also have a couple other different ways to get to Walmart on here. You know, we could do something like this. We could take in our numerator and take those resistance and multiply them and then kind of across the bottom. We could do that. And, or we could do this one. All these are the exact same formula. They give you the exact same thing, just different ways to math it out. So I like this bottom one, but I have to show my kids how to put it in their calculator. Okay. So when you're doing that, and I always come over here with my kids now and I say, okay, make a note here that right here, less than the least. Okay. A little double check for us. A little, does our answer make sense? Is that our resistance total is always going to be less than the least amount when we're talking about these. Okay. All right. Any questions about any of that stuff so far? Okay. All right. The next thing we're going to do is break down a series and parallel circuit. What I'm going to do is I'm going to draw a series circuit. We'll say 12 volts, and I'm going to say 300 ohms, 400 ohms, and 500 ohms. Okay. And then I give my kids this the same way every single time. We're going to say voltage total, current total, resistance total. And I've seen different charts of this. And then I'm going to say the voltage at resistor 1, voltage at resistor 2, voltage at resistor 3, current at resistor 1, current at resistor 2, current at resistor 3. Put those blanks, and then we'll say R1, R2, R2. Nobody. Okay. Thanks, Caleb. So go ahead and draw that down. It is time. I want to take a break before we do this. I know it's a little bit early because we're going to go for another 30 minutes or so. So let's go ahead and do this. Let's go ahead and take it's 4:33. Let's come back at 4:38 and then we'll break this down. So go have a Coke and a smile, 5 minutes, and we'll come right back. All right, welcome back. So what I like to do with my students on this is go through a kind of a step-by-step process with them. And it's going to be a little bit hard for you to kind of see my calculator, but I'll try to kind of show it to you as we go. And just kind of the first thing, like any of these problems, is we're going to write down, you know, the knows, and then kind of look for our need to knows, right? And so, well, what does it tell me? Is it tells me my voltage total is 12. And then I know the resistor value of each of these. And I just kind of work clockwise around that. It's pretty standard. Okay. So one of the rules, and I'm just not realizing I kind of forgot to say this, is that when we use this triangle, I make a rule for my kids: must be in base units. So, because I can't take volts times kiloohms, or I can't take voltage divided by milliamps and get the right answer. So we always want to convert back to our base units there. So when I look at this and I say, okay, so what's my first thing that I can do here is, well, I can look at my series circuit formulas and I can say, well, I've got all the resistors, and to find the resistance total, I can just add those up. So we can just add that up, and 900, so that should be 1200, right? Oh, I wanted to do that in red, sorry. You can see it, 1200. Or you might tell the kids they could also put 1.2 kiloohms would be acceptable, right? So they're going to add that up, and then so step one, let me just go ahead. So I'm going to tell my kids step one is to add resistors to find the resistance total, right? And you might even, sometimes you can make a note over there is, you know, did you have any, you know, double check SI prefix. Make sure you didn't, you know, if you had, if one of these, a lot of times they might try to sneak one in that's 1.2 kiloohms, and you've got to convert it to 1200 before you add it up, right? So, you know, that's the, if they're going to make a mistake right there on that, that's what they're going to do, okay? So next, my next step when I look at this is I can say, okay, well, when I look at my formulas, what can I do next? Well, I've got my voltage total and my resistance total. So I can take my voltage divided by resistance and I can find my current total. So with my calculator, I can say 12 divided by 1200, if you need the calculator for that. And we're going to say that that is 10. Oh, I wanted to do red again. 10 milliamps, you know, or you might say 0.01 amps. Either way, I kind of like to write those at the beginning, just if they're switching back and forth to kind of help them with that. Well, so step 2 is going to be to use Ohm's law to find current total. Okay. Step 3. And if I write below this, somebody holler at me. I'm bad about doing that because I'm not watching that screen. Step 3. So when I look at this and I go, okay, well, what else can I look at? Well, in a series, what do we know? The current is always the same. So if I know the current total, I can know the total at any of these. So I can go ahead and fill that out. So fill out current at each resistor. Okay. And they're all the same, right? Same. Step 4. Use Ohm's law to find voltage at each resistor. So when I go back to my Ohm's law, I'm going to take this multiplied by that to find this multiplied by that to find this multiplied by that to find that. So, and of course, this one, some of you don't need to do the math, but we'll put it in and we'll say we've got 3 volts. And then on the next one, we've got 400 times 0.01, 4 volts. 500 times 0.01, maybe 5 volts. Okay. Step 5. And we didn't really talk about this yet, is we're going to use KVL, cross voltage law, in a series to double check. And so I'll write that. What are we doing? Well, I'm taking the voltage at each of those. This, if we didn't say, we didn't really identify, is KVL, okay, in a series. So we're going to use that. We're just going to add these back up. So I'm going to say 5 plus 4 plus 3 equals 12. So does that match what we had earlier? It sure does. So that thing discount double checks. See if I can get that all on one paper. Now, here's the deal. Here's the deal. And so Shane, if you're not familiar, like if I hadn't have just kind of picked these, if I'd have put 440 or 550 and I didn't have these nice, easy numbers, right? I might have gotten, depends on how many decimals I wrote down on my current. And I always tell my kids a good rule of thumb here is to try to keep 4 numbers. So like an example might be 0.01358, and if they do that, when they add them back up, they're going to get pretty close. If they got 11.98, 12.01, that's close enough, Steve. Okay. Because most of the time it's just going to be that they didn't carry all the rounding. They're going to be fine. They're going to be fine. Just tell them that they've got to be close on that when they add it back up. Questions about how to do this breakdown? All right, well, let's move on to the parallel one then. So go ahead and it's the same values that we had. Before, so I'm just gonna start, and I'm gonna fill out what we already know. And while you guys are doing that, so when I'm doing these in class, we're going to do a little gradual release of responsibility there. We're going to work a couple problems on the board. I'm going to have them with their whiteboards. I'm going to have them plugging that stuff into their calculator. And I'm real fussy about everybody kind of participating. So I know that everybody can do it because, there's nothing worse than getting a B on a test because you didn't know how to plug something into your calculator. And so make sure that everybody's following along, because with this kind of step-by-step algorithm that I give them, they should hopefully be able to just kind of reproduce that. And especially after we go through it a couple times. And then so we'll do it, I do it, we do it, you do it kind of deal, and let them kind of double check. And then I give them some practice, maybe I just draw one of these out on the board and have them bring me the answers back tomorrow. And that's one of the things that I do. And kind of, we've had some people in here that are some math teachers. And so one of the things when we're doing the activities, I may try to chunk this up and just give them that series circuit that day and have them, we do the I do it, you do it, we do it in class. And I may have them just come back and give me and just show me that they worked this for full, and as long as they attempted it, they're going to get full credit. And but they got to show it to me right when they walk in the door, so I'm standing there at the door checking their papers off, because for me, one of the things that I hated about math is if you had 20 problems that all work the same skill and you didn't know how to do it, you did all 20 of them wrong. Well, that doesn't help you learn it, right? So I always tell my kids it's okay to break as long as we know where we're broken so we can fix it. So I want to let them go home, try it. If they, they've got a video, they can watch me going through it again. And if they can't get it, then I want to catch that and try to correct that, whatever misunderstanding they've got right then, so we do a lot of that with the simple machine practice problems, any of the kind of the math skills that I teach. Okay. So step one is really the same as before. Here is we're gonna add up, or no, we're gonna find our resistance total. The deal on this one is the different formula, right? So I gave you the different ones there and then here. So and when I do this in class, I actually kind of write this out on I'm gonna say, okay, in your calculator, what are you gonna do? When we're looking for this formula here, how are we gonna do that? So we're gonna open parentheses, and I'm gonna hit 300 inverse 1 plus 400 inverse plus 500. So I'll show them this. And then the key is to not forget the last inverse. This is the mistake that the kids get. So when we put this in our calculator here, we go 300 plus 400 plus 500, close parentheses, inverse. And I get something. What was the rule on that? What should my answer be? What's my double check for resistance and parallel? I wrote it down on the other sheet in purple.
Less than the least.
Less than the least. So my least is 300. So I know it's going to be less than, and here's the other one. If you forgot this, if you do this math and you forget this, you're going to get a number smaller than 1. So if you get a number smaller than 1, yeah, that's less than the least, but that's not right either. So somewhere I always tell the kids, somewhere between 1 and the smallest is typically going to be right. If you get a number less than 1, you just probably forgot this. Or if you're using the other formula, you forgot the 1 over, right? You just forgot to take the reciprocal of that last deal. So we get on this 127. You can see that what I got, 127.65. So I'm gonna write 127 point, we'll go 6. We'll go 66. Round it a little bit. So that's step 1. Step 2, just what we did before. Step 2 is going to be to use Ohm's law to find current total. So we can do that. That is voltage divided by resistance again. So I'm going to take my 12 divided by my 127.66. And I get I'd like to keep a couple of these. We'll go 9399. So, whoops, I wrote that in the wrong spot. Pardon me. 99, 9399. If you can read my calculator there. What I got. So I'm going to do that. Now, what else do we know about a parallel circuit? So if we go back to, we're going to do my formulas. There they are. We go back to in parallel. We remember that our voltage was the same no matter where we're at. So we can go ahead and fill that out. And you could have done this at the very front too. You could have just, if you might train your kids to do that as well. So we're going to copy our voltage. Total to each resistor. Right. So step 4 now is going to be to use our Ohm's law to find our current at each one. So step 4, use Ohm's law to find current at each resistor. Okay. So first one, 12 divided by 300. I think I see a pattern. 12 divided by 400. 12 divided by 500. Last step is going to be to use Kirchhoff's current law to double check. So I'm just going to take those currents and add them up, because that was what our, so if we didn't make a note on this, this one is current law in parallel. So I'm going to add those up. And this is where if you can keep for, you know, the more kind of numbers, the closer you're going to get kind of deal. So add all those up. 7, 9. So we go back and what did we get? We got earlier, we got 9399 and now we got 94. That's great. That double checks. We're good to go. Okay. That's close enough for what we're doing. Okay. So by giving them that kind of step-by-step breakdown, it really allows my kids to kind of, now then later on, maybe on the test, instead of giving them voltage total here, I might give them one and I might say your current is 0.034 amps. And I don't even tell them how to break it down. But could I give them that? Could I give you that and the resistance total and you still fill out all these blanks? That you can, you just have to kind of go a different way. So that's a good check for them there. Okay. So that is the physical part of this. All right. Let's take, it's 4:58. Let's take 5 minutes and we'll come back and we'll build some stuff in Tinkercad. Okay. Five oh three. All right, there we go. If you don't, I'm going to share my screen with you and we're going to be working in Tinkercad. So tinkercad.com. And when you get here, if it doesn't bring you to this page, you can just hit on the little Tinkercad logo and it'll bring you down where you can click on circuits. Okay. So you can click on circuits here and create a new circuit. Tinkercad is cloud-based, so sometimes it operates a little slowly, but it should save everything. You can change the name of things, just so you know. But if you don't, it's going to give things a very weird name, like whatever that is. I don't know. But I'm going to create a new circuit. At least I think I'm going to. And I'm going to build that same exact series circuit that we just built. I'm going to build those exact same circuits, okay, that we built. So now you can either try to click along with me as if you want to and build this as we go, or you can just try to watch. It's up to you, okay? But don't be afraid if you are trying to click with us that you know, if I leave you, holler, okay? Because I can't necessarily do it without the verbal kind of cue that I need. All right. So the first thing I want to do is I'm going to grab a small breadboard, and this is the exact same one like you guys have in your kit. I'm going to drag that out here. The next thing that we want to have is, now I think in y'all's kits, they just gave y'all some battery. Did they give y'all batteries, right? They give y'all some batteries, not a power supply. So so when you build these, you can build a power, but I'm going to show you where the power supply is at. I got to switch from basic to all components for this. And I can just type in power, I think, power supply. Click on that. Oh, there it was. And it's this guy right there. There it is. And I'm going to change my voltage to 12. What we said we were going to use. Now I'm going to go back to basic components. So I had to switch to all on that toggle switch right there to get the power supply. Now, this thing right here, if I wanted to rotate it, which I do in this case to make it a little cleaner, you can see we've got, you know, if I wanted to delete it, if I wanted to make some comments about it, lots of different things. But I've got this rotate right here, which I think you can also control R. If I click on it, it puts a little blue highlighter on it. Nope, not control R. Just, I wish it would rotate both. You could choose which way you want to rotate it. And 12 volts is what it is. So I can double check it. If I wanted to change the voltage, I could do that. I could name it, whatever. And the way that I like to do these is I like to try to set them up as close to the actual schematic as I can. So if you remember on this, we had like positive coming out of one side of the battery and negative coming out of the other side. So I'm going to take my negative and I'm going to run it up here to this negative ground rail. And I like to try to make that wire black for negative. And then the red one, I try to go to the red positive down here, and I'm going to try to make that one red. So I've got those two things kind of set up. So remember on these breadboards, now I've got power. If I just click on that hole, I've got power run all the way down what I'm going to call the power rail. And I've got ground run all the way, or negative run all the way down the rail up top. I've got mine in a little bit, you know, I've got it kind of, you know, landscape orientation. So what I want to do now is we have 3 resistors, right, in series that we had in that. We had a 300 ohm, a 400 ohm, and a 500 ohm. So our components cannot be in the same connection point. Like, so, right, if you, like, there's a metal strip that connects all of these that are highlighted together. So I couldn't take a resistor. If I put a resistor like that, and it's gonna, the electricity is gonna take the path of least resistance, right? It's gonna run through the metal strip in the bottom and not through the resistor. So it's not doing any good. So I've got to have all of these resistors jumping those gaps that I told you about in the breadboard. So there was 3 of them. There's one between the power rails and the main board, and then there's the Grand Canyon in the middle. So I got to have my resistors going from here to here, one across the middle, because it just, I have 3 of them. So I'm going to do it like that. Could I do it a different way? Absolutely. But that's the way I kind of teach my kids. So I need to go to my round rail, and it doesn't matter. I could go here or all the way down here. Doesn't matter. I'm just going to pick right there. And I'm going to grab another one, and I'm going to be in the same, you know, column, so to speak, in this orientation across my Grand Canyon. And then I'm going to place the 3rd one from my power rail into that same. And then you can do it as you go, or I can come back. It always defaults to kilo ohms. So when you're selecting these, you could either, you know, like this one is 500, right? So I could put it in as 0.5. That works great. Or, you know, like this one was, what was our second one? It was 400. I could put 400, and your kids probably will feel better about this. And I could say ohms there. That's a mistake that kids make. So always double check them. If they get one they're getting funny readings on, make sure that they, you know, they didn't put in the wrong deal. And this one was 300. And I always tell the kids, if you're ever in doubt, you know, like if you see this one right here on the coloring, and we didn't really talk about that, but the colors mean something. I don't get into that a whole lot in POE. Just so you know, let me, while we're talking about it. Where is that? I thought, oh, there it is. Put this in the chat for you. It's a website I give my kids where they can easily use that to kind of double check their resistor values. All right, so I've got those all set up correctly. I can double check on them to make sure that they're correct. I've got everything hooked up. I didn't use any hookup wires the way that I've got this set up. And now if I hit play, the telltale that my circuit is working is that, you know, my voltage reads 12 and I've got a current reading. And we've already done the math on this, so we know that current reading is correct. So we know that we've got this circuit hooked up correctly. It's right here is the current total for this circuit. It's reading exactly what it should, we're good to go, okay? So, and notice I didn't put the button in it, okay? No, the button, like when you build these, is just a little bit hard to kind of hold and everything. Now, I will say this, then the next thing we want to do is we want to learn how to measure each one of these things. So we've got a multimeter that's all the way down at the bottom. We already have our voltage total and our current total. All right. So we already have those on our power supply. If you buy the ones for POE that Project Lead the Way says, they've got RSR has a couple of little cheaper power supplies. I just found out this year, so this one's like $23. They got another one that's like $3 more, and it also looks just like this, and it also has the current display on it. So we'll talk about that when you're ordering materials, but I've a better way to do that. But if I didn't want to measure current, if I wanted to measure the current with my multimeter, I can do that, and I'm going to show you how. And real quickly though, before we get too carried away with that, I'm going to go. I'm going to put a document in the chat for you that's called the multimeter cheat sheet, and you can